decided we would keep the session open. And I think what we're going to do is very interesting. We're going to give you some information on what's been going on the last 2 days in the Foundry. You've probably seen smoke and fire coming out of one of the rooms back there. We had a 2-day very intriguing session. And the Foundry was set up to make things happen. And I think we have seen some very interesting things happen in the Foundry. And I believe as a result, the Foundry will be a continuing feature of future National Space Society conferences like this. The lady that really made things happen is going to now tell you some of the results of the Foundry. It's Laurie Wiggins. She's with the Boeing Company. She coordinated all the planning and activities here for the Foundry. And I was just sort of the honorary chairman along for the ride, but I learned a lot and I really enjoyed participating. So without further discussion, let me introduce to you Laurie Wiggins, who will tell you what happened at the Foundry.
Okay, let's talk loud. Good morning. Like you said, I'm Laurie Wiggins, and with a great deal of help from the Foundry Development Committee, I ran the Foundry workshops on Saturday and Sunday. What is the Foundry? I've gotten that question continuously during this conference. So for those of you who are already aware of what the Foundry is, just bear with me while I run through this briefly. The Foundry is a way to turn good ideas into doable projects. Greg Allison, the ISDC conference chair, and I came up with the idea about a year ago, and I've been working on it ever since. People with project ideas, we call them participants, bring ideas to the Foundry that they want to develop. We provide a structure for them to work within, a place to work, and resources, which include other people at the conference, as well as some data we brought along on how they can obtain funding and so forth. The major events during the workshop were, on Saturday morning, the participants presented their ideas. They had 6 minutes to stand up there and give a brief overview of their idea. And I had to be pretty strict about the time because we had a limited amount of time, but everyone was very good-natured about it. On Saturday afternoon, and Sunday morning, they worked on them. And so we had the chairs taken out and tables brought in so that people could work around tables and have discussions and hammer out their ideas. And they most certainly did that. Then on Sunday afternoon, the participants presented what they had accomplished to a 3-person panel. What I had asked some people to do was to come in and form a jury, people whose judgments and track records I trusted and were well acquainted with. And these are good heads, good people who have a lot of experience in the space business, either from a business and or a technical viewpoint. And so we asked them to come in and to listen to these ideas that these people had presented. We had asked them to work through certain questions during the weekend, like what is the goal of your project? What are the major tasks? What are the resources that you think you need? What are the problems you think you're going to encounter? And we encourage them to bring up any questions that they, or problems that they still had at the presentation in front of our 3-person jury, so that we could help them work through it, because this jury was provided as a Foundry service, as an additional way to be critiqued, always in a constructive way, but still to obtain additional help and feedback on the project before they were launched out into the aftermath of a conference to go do it, to actually go and do these major tasks. And and to run into the problems that they may have foreseen and some of which they didn't foresee. On Saturday morning, we had 24 people present ideas on how to increase awareness of or access to space. And this was a criteria for Foundry support. You had to show that it was space related. And of course, we anticipated that phrase would be interpreted broadly, indeed as it should. The range of preparedness was very broad. However, it was obvious that some people had given a great deal of thought to their ideas and that they were well prepared to carry them further. Another benefit of the presentations was that other people could discover who was working on what, and indeed there were people who had very similar ideas, and so we had some collaborations take place over the course of the weekend, and that was very exciting to watch. I'll get into more details about that in a minute. On Sunday afternoon, now remember we had 24 on Saturday morning. We had 8 projects presented to this review panel I was just describing. Further discussion, so there was some fallout. Apparently, several of the Saturday morning participants were unable to participate. There were other things going on at the conference and so forth. But I was heartened to see that at least a third of them were willing to work through the weekend on this project, on their project. However, the 8 projects that are left, we feel, will continue in the months to come. And they are, I just want to describe it briefly. One gentleman had a project to save a planetarium in the local Lehigh area in the Lehigh Valley of Pennsylvania. A high school that this had been built next to is on the same campus. The school board wanted to shut it down and or cannibalize the equipment, which was worth several $100,000 because they're facing budget problems. And this gentleman, he's not a teacher, he's not even connected with the school system. I think he works at Bethlehem Steel. He decided that this was worth saving. And so he was one of the most diligent participants. He really worked through all the steps that we asked him to, and he really did some very good project planning, and he presented it to the board, and we had a lot of ideas because it turned out that someone else had had a similar experience and could share that, could share their experience and the subsequent outcome with them. The second project that was presented was a way to increase the usefulness of the Space Studies Institute information matrix, Space Information Matrix. This is a database that 2 people in the Space Studies Institute had worked for several years on. And basically it was a way to cross-reference research in different areas with who was doing it, and via this database to show critical paths to space. In other words, what sort of research you needed to have routine access to space, live in space, and so forth. What areas of research might come to light that you were not aware of as you plotted this critical path using this database. Most interesting, what they really need now is data to fill it. And that means people scanning scientific journals and books and so forth and inputting data into the database. So she was looking for some help there, and I think we gave it to her. A gentleman wanted to develop a probe to sample dust at the L5, the stable L points. And obviously this is quite an undertaking. And for anyone, that would be an enormous undertaking. So in this particular case, we indicated to him that this was an awfully big ball of wax to try to get your arms around. Why don't you chop this down into doable steps, which is one of the things the Foundry helps people with. It helps them scope their projects. And hopefully he'll be writing a paper on this, which is the first step to go sell this idea. Another project, this gentleman is very interested in exoarchaeology. And what this is, it's the study of human or other visits to other planets or extraterrestrial visits to our planet. And this would be a scientific study. Also, the study would include the change of position of the planets over time. There are ancient records that contain information on position of the planets and how they've changed over time. And so he's very interested in pursuing that also. He also wanted to develop a newsletter in conjunction with that. And so I think we were pointing him in some areas he wasn't aware of before. A gentleman presented an idea to develop a scramjet engine. And this is a new concept, a new and better way of doing it. And he is now involved in a collaborative effort. That collaborative effort will be described to you after I'm finished. I don't want to steal their thunder, but I'll just mention that. In addition, a launch vehicle manufacturer and another engine builder have gotten together, and these three gentlemen will be talking with you after I'm done. Yet another project dealt with the formation of an investment fund for a space project. We also had another project along those lines. A gentleman wanted to start a bank. He's a banker, and he wanted to start up a bank that would eventually invest in space projects. And so the investment fund person and the banker were talking. They had some conversations. I don't think there's a collaborative effort there, but their efforts are complementary, and I think it was still very useful for them to be able to know about each other and to exchange ideas. A gentleman who was already involved in the business, I think we helped him along. He was involved in building amateur rocket engines, and he had already was looking at establishing a business to do this. And so I think for him, basically he had a place to work and a place to exchange ideas because his idea was further along than most other people's. And then we had a member of the jury who turned out wanted to start a space magazine for children. And it turned out there were several people in our group that had already had experience dealing with children and exciting them about space. So I think the feedback that he got was very helpful. So all in all, it'll be very interesting to see how these projects move forward in the months to come. And although there may very well be a mortality rate, we are hopeful that within a year that most of them come to completion. And we have developed a newsletter. The Foundry will be putting out a newsletter to status them about every 3 months. You will also see more Foundry articles, and we hope to keep promoting the idea of the Foundry. It's really a place for doers. If you're interested in working the problem to get to space, the Foundry is for you. Thank you.
Any questions, Laurie?
How can we stay in touch with the Foundry?
Well, see me.
Okay.
Anything else? Yeah.
Are you talking with our Toronto people and people in Cleveland for a couple of years down the road, continuing this?
I've already, actually, the Toronto people have already been in contact with me, and the plan is to have the Foundry workshop at Toronto rather. No plans beyond that. Any other
Certain Cleveland will give you a warm reception on the idea.
Thank you. I hear that, and I'll be talking with them. Are there any other questions? Thank you.
Thank you, Laurie. Appreciate that. I think it's very appropriate that the example project that we're going to present this morning relates to transportation, space transportation. Since track 2 has sort of followed that theme all during the conference. And the speaker and participants are right here on the front row. Let me introduce them. James George, who is with Truax Engineering. Are you going to be the main?
I'll be the main talk.
Okay, and then the other two gentlemen, if you'll stand up, James Hopkins with Orbitech, and Roy Harkin with himself, I believe, here in Huntsville. So here we have California, Arkansas, and Huntsville all collaborating on a mutual project you're going to hear about.
All right, now I'll warn y'all right now, I'm a salesman, not a tech, not an engineer, I'm a salesman. I will take your children and sell them back to you, no problem. At Foundry, I was trying to get some ideas to get better funding, better approach, partnerships for CLAR. If y'all are familiar with it, Sea Launch and Recovery Vehicles. I represent Truax Engineering out of Oceanside, California. And with any endeavor, funding seems to be the main reason everything stops. We have a number of things that we're going through in building the vehicles. The great thing was tying up with James and Roy, because all three of us represent independent sources of funding. It's tremendous opportunities. So what the project now entails is not just having CLAR developed in California, but it is an integrated effort that we're going to have partners and a collaborative effort here. We're going to be establishing what we consider a propulsion shop. Truax Orbitech Propulsion Systems Incorporated will be established in Little Rock to take advantage of some funding available there, some infrastructure that is available there in the way of test stands, and it doesn't hurt that it's in Uncle Bill's yard. Now, in addition to that, we're getting to talk to some of the other partners, such as Wiley Laboratories, about some ideas and some things. And I expect that within a year, we're going to be finishing up well, before the end of this year, we're going to have a proof of concept launch on a CLAR vehicle, which is basically just a single stage corporal. We'll be popping that one off for amateur. That gives us a lot of information necessary to complete the applications for the Department of Commerce licensing for suborbital launches. Before the end of next year, before the end of 1994, we will be operating two-stage suborbital sounding rockets for microgravity research. And we'll be concurrently developing a nitrous oxide methane liquid fuel engine. We'll be concurrently developing a plasma engine. He told me to eliminate the word fusion. That's much, much later. We have concurrent projects of other propulsion systems that this shop is going to turn out, which really I like because I'm a salesman. If I have a family of products to sell that have known markets, everything that we're addressing is a known market, a provable market, then financing is easier, sales are easier, and it's much nicer to have something coming in. It's much more like a business. So, all I can say is y'all stay tuned, and I'll be happy to try to answer any questions that someone has about this project. Too easy on it. Okay. So, like I said, yes, Laurie.
Where will the vehicle integration be done?
That'll be done in California. The reason we have Oceanside, Long Beach, and Little Rock Propulsion. Oceanside is corporate vehicle construction. Integration will happen in part of the phase will be in Oceanside, and then of course the fuel load and payload will be finished in Long Beach because that's where we're going to be having the port facilities. The smaller ships, the two-stage sounding rockets, I anticipate putting on in an ocean-going tug on deck, and then we take them out to the launch site, crane them over, balance them down, and launch them off that way. So all integration will happen on board the tug. But since it's a LOX kerosene engine, people don't really want you pumping LOX inside the port. Also, that's too much of a risk of it boiling off too much of the oxidizer, so it doesn't work properly. So we'll wait to do the final fueling of LOX once we're out on site. So it's almost like a three-stage integration. You've got vehicle and payload, then you've got installing it on the tug vehicle, then you're going out to the site and dumping it down. And the big reason for CLAR, as everybody knows, is one, you get to reuse the system. It's totally reusable. First stage and second stage, flash it down, tow them back in, got it to begin. Secondly, what kind of orbit do you want when we're in orbit with vehicles? If you want a polar orbit, we can go for there. If you want an equatorial orbit, we go for there. And the scheduling is a lot easier since we're not dependent on government ranges. We don't have government range costs. We have reduced liability because we're out in the middle of the ocean. We're going to hurt. And we have a lot more flexibility as far as scheduling the launch. We just have to make sure that the weather's good. That's more like the Pacific Ocean. Yes, sir.
You said Pacific Ocean, how far do we go out to sea?
It's going to depend on the mission, sir. If it is just a suborbital, then we calculate the worst case scenario on how far it goes in powered flight, and we make sure we're that far from land. When it's an orbital launch, we're going to have to figure out what type of orbit they need, where they want to be inserted, and we make sure that we have the range clear for downrange on that. I anticipate we'd be about a couple to 300 miles out and a little bit farther south. So it's going to be, take the coast of like Baja, Mexico, and come out a ways. It'll be down in that area, nice and quiet.
So if you launch towards the east, you think 2 to 300 miles is far enough off?
That's going to depend on the vehicle and payload. If it's a small suborbital, it's going to be way up, I mean not a suborbital, but a small SAT insertion, this is going to be a much smaller vehicle, and it's going to be up real quick as compared to like the larger version that'll carry anywhere from 10 to 100,000 pounds. We can move farther back out so that we have a longer, much longer range capability. Yes, sir.
It was mentioned you're working on a scramjet engine. Could you tell us about that?
I can. Roy, good.
We have the time if you're willing.
Pardon me? You're the advanced propulsion design team. How much do you want to talk about? It's an interesting concept, and I don't know how much Roy really wants to talk about it.
Who asked the question?
I know.
Okay. Basically, all it really amounts to is, not getting too much detail, it's allowing it, possibly using it from zero velocity, standing start, using compression waves from plasma or ionized gas to compress the airflow in the engine to allow a pumped compression instead of having a turbine system for an engine. Also allows for shaping of the airflow at higher speeds to increase the efficiency. That's pretty much how it works.
Is it a pulse detonation engine? It's a pulse detonation engine?
Pulsed in the beginning. It's similar to a pulse jet at low speeds.
From the people that we've talked to that are intimate with the technology and working on it, there's no showstoppers. So that's why it's the advanced propulsion team. We're not sure exactly the time frame of developing it, although we expect to move very rapidly. It's still, whenever you're designing something new, there are unknowns. So we have no true timetable on a commercial product, but we got our own ideas.
So you're going to test it using sea launch concept?
More than likely, the original, once we're into a stage where we want to try to test some of the things, we may be using some of our own suborbitals to get some final testing done.
A lot of static testing first.
Yeah, a lot of statics. This is one of the nice mixes. I mean, what you've got here is a joint venture, if you will, of a launch vehicle, integration group, payload specialists, and propulsion specialists. So it's not one company saying we've got to do everything. It's different groups saying, let's put our talents together. That's what I really like about it. And Laurie, it was all your fault.
Before you leave, I think James Hopkins would like to say one word about his propulsion system. I think it's somewhat unique, and you would do.
The methane nitrous oxide motor, the beauty of this system is that it uses very cheap fuels. Both propellants are readily available in industry, and the exhaust products of it are nitrogen, carbon dioxide, and water vapor. Therefore, it is environmentally friendly. And due to the nature of the fuels, it is scalable depending on how much propulsion thrust that you want. You can scale it up or down to achieve that kind of propulsion.
What are specific you expect? What specific impulse?
It comes in at around 275 to 280. So it is competitive with the specific impulse of the monomethyl hydrazine nitrogen tetroxide motors that are used by NASA on the space shuttle, which anyone that is familiar with rocket fuels know that those are both highly unstable, and the toxicity of exposure to them is like, if you smell it, you're overexposed and you're possibly going to die. And like I say, both these propellants, they're used throughout industry. You have methane being pumped into your homes every day to provide heating. You go to the dentist and he gives you nitrous oxide to make you relax while he works on your teeth. So
Do you use also hydrogen in upper stages?
what?
Use hydrogen oxygen in upper stages.
We have no design for a hydrogen
No.
oxygen.
At this
You wouldn't
point,
use the idle tank?
Pardon, sir?
You wouldn't use the idle tank?
No.
no, we had no plans for that. The applications that the hydrogen oxygen engines are looking toward nowadays seem to be for orbit-to-orbit transfer type applications. And we are looking at some more advanced type engines for those applications in the future.
So basically, with two chemical propulsion systems. The CLAR is primarily LOX and kerosene. And then with the nitrous oxide and methane, the idea is to address very specific understood markets for not only boosters in the second stage, payload engine, and also station satellites. Those are the areas primarily that we anticipate using the NOC, the N2O CH4 engine.
Any other questions?
But we'll be running
Information on
those.
recovery.
Pardon?
Information you're recoverable, how you really recover?
The vehicles enter and with either a drogue or a torus ring, it'll inflate towards the end of before its impact, which will give it a nose down aspect. We're building these in shipyards, by the way. So it's a very sturdy system. Very unusual because they're not exotic metals. So it comes down, hits down. We've already been doing drop tests, so we know that they're going to be recovered. Embarrassingly to say, in 1962, the United States Navy did tests on an Araby sounding rocket. Took it out off Point Magoo in California, launched it, came back down, they towed it back in, hosed it out, nothing was wrong. 3 weeks later, they refueled it, took it back out, launched it, recovered it, nothing was wrong, hosed it out, let it sit. A couple of weeks later, they took it out and fired it again. An expendable sounding rocket, they got 3 launches out of it without any serious modifications to it. That was in 1962. See how far we've come in 30 years. So we know the concept works. We know that there are design considerations to make sure that when it does re-enter, it re-enters nose first aspect, and that it does take the impact.
Did anybody serve in the Navy for you all?
I was an officer in the Navy for 6 years, 3 months and 12 days. Starts at midnight. It was even. Robert Truax is a retired naval captain, and is basically the design father of the Polaris missile. So we're very familiar with saltwater missiles. Absolutely.
And on the propulsion side, I was in the Air Force for 6 years, 5 months, and 19 days. He was in 4 years.
So yes, we have military experience. It'll be helpful. Like I said, it's Laurie's fault that we're doing this, and y'all stay tuned. It should be a lot of fun. Thanks.
I might mention, I have a little military experience. When I heard they planned to launch a Corporal rocket again, I got excited because I launched a Corporal rocket 40 years ago this year. I didn't watch that. I'd like to go see it launch again. And I might also mention that Wiley Laboratories, who I work with, are very interested in this program. We're going to be talking to this group as a potential team member, supporting the testing, which Wiley does so well. And we also are heavily involved in payload development and integration. We have a space furnace going up on the next shuttle launch, SpaceHab first mission, which is a commercial payload. So we're very interested in the application of these systems for sounding rockets and for putting small payloads into orbit and recovering at a much lower cost than putting them up on the shuttle. So we see an exciting future for this kind of joint venture. Look forward to working with this group. Unless anyone else has a subject on the Foundry, or okay.
Well, I got a map which I presented in the space station meeting. They got 8 people that I'd like to share with you.
Okay, come right up. If we have time, if we have a wild card. You can get it, you get around.
I got a space station. I get a space station called Oasis. And Oasis stands for Open Architecture Space International Station. And I will show you a few charts here. This is the mission profile. The mission profile tells you a lot about the vehicle which is being used. It uses the repositioned external tank. The external tank is the cheapest unit on the space shuttle. To give you some ideas, the external tank is about $10 million. The solid rocket motors per flight are $18.4 million. And the orbiter and its system work per launch is in the order of $200 million. So the idea is to get the cheapest unit to make an effective change, which is tremendous payback. They're talking about a saving compared to Space Station Freedom in the order of $20 billion. The launch is accomplished like this. It's 8.5 meters tall. The solid rocket motors are staged as today. And there's an additional part which is a yoke, which is a thermal and acoustic shield against the back. It uses an aft cargo hold, which is sizable. The whole thing goes in the near orbit. The external tank is jettisoned at MECO as today, except from a different position up front. And the orbiter has on its belly strapped on a high-volume space station, twice as much volume as today. There are 3 RL-10 engines on the space station core, which injected into orbit. The station is manned right on the first launch. There's a brief checkup taking place to see if everything is in order. Then the orbiter separates from the attachment points, redocks, as the station transfers the crew, and the crew ascends into orbit. And what the kind of space station we're considering here is something like this here. This is Oasis 1. This is the aft cargo hold. It is huge. It's at the 1,500 cubic meters. Here's the Canadian manipulator arm. Here the 3 RL-10 engines. Instead of modules, I attached cupolas with visibility for the Japanese and for the ESA. And there's a berthing port back here. There's a huge airlock, so you can also transfer racks, not just tow modules. In comparison, there's another gross version for more power. You put the international modules on like this. And here's the launch configuration. And I like to point out a few things. My background is dynamics. The oxygen tank is in the same axial position as today. And the oxygen tank is the heaviest piece. It's 6 times heavier than the hydrogen tank. Today we have the hydrogen tank in the back here, and the hydrogen tank was involved in the accident at this Challenger. The hydrogen tank shrinks tremendously, imposing the solid rocket motors, pre-bends them. They get bow-shaped like this before launch. And at the release and launch, they twang real hard and exercise the joint about here, which caused the accident last time. We have fixed the seal today, but the twanging is still there on solid rocket propellant, which should not, the solid rocket propellant doesn't like to be twanged hard. But this aft cargo hold doesn't cause that kind of a twanging because it doesn't shrink. So the oxygen tank is in the same positions, therefore the pressures on the SSMAs are the same. The hydrogen tank has now a bigger fall line, about 40 meters, which increases the pressure on the engine by about 33% at 3 Gs and 11% at 1 G. This is not detrimental. The hydrogen pressure can be improved. There's no problem on that. So dynamically, the center of mass is about the same point. The bow shock is way up front, and this is also beneficial. you're reducing your drag by that. The center of pressure for overturning moment has advanced a little bit by pulling this one out from 56 feet to 85 feet, from 56 meters to 85 meters. But this is not an advantage. The center of gravity is controlled, but we expect less reaction control here in the back. You might ask yourself, what is the impact on the launch facilities? Very minimal. The footprint is the same. You're standing on the same solid rocket motors. There's a lighting mast on top of the launch facility, which has to be lengthened because this vehicle is taller. But I want to remind you, the Saturn V, which was 100 meters tall, was launched in the same facility. And this is less. And if you look at the comparison with the Skylab is of interest. Here you see them side by side. And the power, you get more power here. Electric power talking about. And here's the configuration where there's when the solid rocket motors have been staged, you see the core exposed. This is the second stage configuration as you do today, except the hydrogen tank is up front. Here's your core station with the stocking ports, non-deployed solar panels, and then eventually you stage here, you drop this piece here, while this aft cargo hold stays attached with the same attachment points we have today to the orbital belly. This is the configuration which is ready to go into orbital injection for the space station. With 3 out of 10 engines here. You see a 3-meter airlock here, the regular airlocks ports as we have today planned for the Space Station Freedom. And what else we got here? Yeah, by having such a vehicle, you have not only a safer vehicle, but a more versatile vehicle. Presently on the orbiter bay, we cannot carry oxygen hydrogen stages for planetary probes. But we certainly can do that in the aft cargo hold. The aft cargo hold is a large hydrogen environment and can use a system tank to collect residue propellant from up front. What I have sketched here is a high power broadcast satellite with a big antenna which is fully assembled. One thing is to emphasize here, we got 8-meter diameter payload area here, 30 meters long. The payload bay doesn't compare to that. The payload bay only has 4-meter diameter. This is the launch configuration after the solid rocket motors have separated. You're throwing off also the lid from the pallet for large payloads. And we can readily fly to the planets in an efficient way. Not in piecemeal, assembling an orbit, for example. I do have a comparison table for all the American space stations we have. But forgive me for scrambling so bad. You guys see it because I didn't think I was speaking today. It happened so about yesterday. This is the comparison. The volume of Skylab 360 cubic meters, Freedom 808 cubic meters, and I took not the IDs, I took the ODs from the different modules. Oasis 1, 1500 cubic meters, Oasis 2, 1800 cubic meters. Diameters are like this. On Saturn V, the third stage, 6.6 meters diameter. Freedom has modules with 4.45 maximum diameters, and Oasis we're going up to 8.23. It's a nice quantum jump. The span, the solar wings, on the Skylab we had 27 meters, on Freedom 75, on Oasis 77, Oasis 2 also 77. The length on Skylab was 36 meters. Freedom Oh, here we are. Freedom, I got 108 meters. The big truss work has 108 meters. On Oasis, as you saw earlier in the picture, 57 meters. When you extend, put the next level of solar wings on there, extending it to 50 meters. And if you would assemble 3 solar panels, as you have in Freedom plant, you will add another, the difference between the two here, which is another 13 meters. So going up to 60. The power generated on Skylab, we had one wing torn off. We had an accident in launch. We had something like 8 kilowatts. Freedom had planned 56 kilowatts. Oasis 1 is one of the Freedom wings, produces 19. If we want to have more, we can do 37, or the full 56 with 3 wings as on Space Station Freedom. Cost, Skylab 2.53 billion. Freedom projected 31 billion. Oasis, we think in terms of 4 billion, and Oasis 2, 5 billion. So that's a wild card because we're talking about major changes. However, the argument is rather simple. We talk about changing an external tank position. The tools are available today, but they can be built by any company. The cheapest part is being changed to do a tremendous vehicle with a fantastic payback. So we can save 20 billion. We can have private enterprise starting their own business, and we're much better off. Thank you for giving me the chance to speak here.
Before you leave, let me apologize. This is George von Pragenau, former NASA engineer for many years, propulsion expert. I think he's got a fantastic idea. Let me just mention the Skylab in today's dollars would be $9 billion.
$9 billion.
You showed the old dollars.
Yeah, that's right.
So actually, you're cheaper than Skylab with your concept.
Well, it's reusable. You
Right.
see the Skylab, you dump the solid flat in the ocean.
So I think it's a fantastic idea, and I want to ask you one question. Is this being considered by the redesign team as a option C? It looks much like it could be.
First, I want to thank you as the society here for giving me a forum at all. Okay, I really appreciate it. I talked to Craig Christenson, and he opened the door for me. And I just accidentally fell in because my daughter was in the distribution of the mail. She put it on my desk and said, I might submit a paper.
Tell us of your problems of getting your ideas across. I think
Well, the
that's-
ideas were around for quite some time, and after the Challenge accident, I was moved to resubmit a proposal of improving the safety of the shuttle to Truett. I was referred back to my parent organization, which is Marshall Space Flight Center. And I made presentations already back in '82. After the Challenge accident, I was convinced I had to tell them something about more capability, fuel launches, more safety. And while I was working, I discovered the safety feature of the twang involving the hydrogen tank. I kept on presenting, but it didn't go many places. And the best break I think I had was Gold Dean, and I sent it to him. So here's the same proposal. And I got a nice letter back from him telling me also that this month NASA has frozen their options. No, but I didn't give up. I went also to MIT and turned it in there. And I haven't been back from them.
Yeah, I did similar things. I've turned in ideas, but they just never see.
Yeah, ideas have a funny way to go. And I don't want to complain, okay? There is a certain way we have to prove ourselves wrong sometimes, and then change course. But the main thing is, on the end of the course, that we got the right solution. That's the main thing. I don't want to complain about anybody because our thinking is restricted certain times, because we want to, for example, utilize the space shuttle to the fullest. And that was a restricting idea. We didn't dare to think about payload integration with the vehicle. That restricted our thinking. But there's this opportunity, and it wouldn't take long to do that.
Any questions?
Yeah, I've got a couple of questions. First one, how would you accomplish the external tank separation with it in front of the rest of the space shuttle? And number two, how do you plan on launching something that's so much larger than the space station modules they've got now when they can't even launch a lab module by itself without having it virtually empty?
Okay. The big difference is this. I didn't show you the breakdown. Even though that the vehicle is 85 meters tall, the external tank today is pretty heavy. It has, I have to show you this picture from the shuttle. Well, I have another picture from the present shuttle. Yes. Notice that about 1.5 million thrust is injected into a critical tank, a hydrogen tank, 35 psi pressure. You cannot afford to warp the sidewalls, so you have very rigid kick rings inside the tank. You have to, as a stress engineer, you would realize you have to design for strain, equal strain, so don't cause stress concentration. And this is very critical. So there's lots of weight tied on in this tank. The tank I propose with the hydrogen tank is on top. The forces are injected tangentially to the tank walls. You're gaining 10,000 pounds. You have less weight of 10,000 pounds in the hydrogen tank. And it goes then further. In the LOX tank will be slightly lighter too, not too much lighter, slightly lighter. They have in total, by putting the tank forward and including the aft cargo hold, you're saving 8.8 tons of weight. So increasing your capacity of launching a payload by something like 20,000 pounds with present propulsion systems. The other gains you have in the orbiter, you have a download limitation. For abort, you have to limit the orbiter in payload, so you wouldn't break the orbiter when you land or crash it. So this restriction is gone. If the payload is the aft cargo hold, it doesn't come down with the orbit anymore. It's a throwaway payload. This way I will be able to lift more, so I lift about 80, I can reach 80,000 pounds lift capability with the upgraded space shuttle. The other thing is, consider that this big volume core is more efficient weight-wise than little, smaller modules with many joints and the truss. So you have lots of more, the structure is by itself more efficient. And being integral, so you're lifting that much weight in the orbit, you don't consider it as a shroud, you consider it as part of the space station. So there's not throwaway. So on several fronts you're gaining performance. And I agree with you, the capability is only 80,000 pounds in one launch, but it's appreciable. You can establish habitability for the space station. So the crew could enter right on the first launch. And notice I had a 3-meter airlock in the back. And what I'm suggesting is when the orbiter makes his visits, it carries some extra racks and gets into the airlock inside this big volume. And then you have IVE, which is intravehicular activity, not extravehicular activity to arrange things. And that's much safer. So that's my answer to your performance.
He asked about the separation of the external tank.
Okay, actually. On the external tank, the separation is here. This is on the side attached, and this is a fender. So you blow the connections here and disconnect the propellant lines right here. Okay? And then you back off with the orbiter with the reaction control system. You're backing off, blowing with the RCS this way and lift away, and return this tumbling with a tumbling valve as it do today.
Can you leave the tank attached as a warehouse?
Okay. The tank has another 2,000 cubic meters volume. And I discussed it with one thing with NASA, because my first proposal was a gravity gradient stabilized, like a bus, gravity stabilized platform. But people advised me about the reboosting. So I was saying, let's go for minimum drag That means you're flying with your station into the velocity vector. So if the orbital velocity is like this, so is your vehicle. Minimum drag, minimize your reboosting. Reboosting can be done either with the RL10s or coming back as the
CG problem.
Yes.
And that's due to the return legs, in case you have to have an emergency return. With your
There's
scheme,
no
you are
concern.
not nearly as sensitive to this.
There's no concern with CG. The CG is much nicer behaved here because the CG is not on the orbiter, it's in the aft cargo hold. So if you have an accident, you save the orbiter, but you dump the cargo.
And you can pretty much take it up fully out.
That's right. I don't talk fully, sufficiently equipped to have habitability. Okay, that's a trick. Because I don't want to show off if I can put at 200,000 pounds. I cannot. I talk about 80,000 pounds payload.
Well, it's much better now than the shuttle because even with the 40,000 nominal payload capability, that gets eaten away with some of the other things you have to carry up, and what you really end up with is 32 to 34,000.
Yeah.
If you look at higher inclination orbits, like 57
Yeah, this
degrees.
is for 51.6.
Oh, really?
And the
Like
RL10,
Skylab.
the RL10 are part of it. Okay? You see, you got a staging picture in there too.
You get much more Earth coverage than you would with the.
That's right.
So if it's 80,000 pounds, 51 degrees of inclination, what is it to LEO? Or to, I'm sorry, to the station orbit, which is 28 and a half.
Okay,
Yeah, it's
I have to say one thing. I'm a trajectory analysis without the RL10s, okay, for 28.5. I put the RL10 recently on it to have the way up. And I have to make some more trajectory analysis to explore.
I was just curious.
I put all the major points in there that we can do it. That's what it is. That was quick reaction.
Any other questions? Thank you very much, Laurie. Okay, since we're wild carding here, I see Buzz Aldrin and Charlie Walker. Do you have any wrap-up statements you want to make, or anything at all? Kind of slow out.
Two in the same deck, that's tough.
Good job.
I don't have anything to add. I'm just real interested to see what y'all have stirred around and what's bubbled up. So
We went
just
through that.
watching.
Did you miss the review of the Foundry?
Yeah, did miss that. But
Laurie is here, maybe you can pass it. I think we've about wrapped up the wild card here, unless anyone else has something. We did turn up a propulsion and launch vehicle program out of the Foundry, which I think is very exciting. Truax Engineering, I know you've heard of them, teamed up with a couple of propulsion houses. Okay, well, thank you very much for your time and attention. Appreciate it. That concludes our session.